Hey everyone, and welcome back. Today we're going on a deep dive into a really fascinating topic, and that's hidden dimension.
Ooh.
Like what if there's more to reality than we can see? Like more than just up and down and left and right and forward and backward. What if there are more dimensions out there? And we're going to be looking at a YouTube video called Where Are All the Hidden Dimensions?
Yeah.
From the channel History of the Universe to kind of guide our deep dive today.
It's a really interesting question. And, it's kind of similar to some other big scientific breakthroughs, right? Where, maybe people didn't believe it at first.
Huge atoms.
Right, exactly.
Tiny little particles that make up everything.
People thought that was crazy for a long time.
Or like black holes.
Yeah.
These cosmic monsters that warp space and time.
Those ideas took a while to really catch on, and it seems like extra dimensions might be on a similar trajectory.
So where do we even begin? How do we even start to look for these hidden dimensions?
Well, I think the best place to start is with Einstein.
Oh, of course.
His theory of general relativity basically changed how we thought about gravity.
Yeah.
He showed us that gravity is all about the geometry of space-time.
Yeah, I remember trying to wrap my head around that one.
It's a big idea.
It is a big idea.
But the key takeaway is that space and time are kind of woven together, and gravity is all about how that fabric, that space-time fabric, is warped and curved.
Okay, so how do extra dimensions fit in?
Well, that's where Theodore Kaluza comes in.
Okay.
He was a physicist who was really inspired by Einstein's work, and he thought, what if we add another dimension to Einstein's equations? What if there's more to space itself than we can see?
So, we experience 3 spatial dimensions, but Kaluza is saying there could be more, tucked away somewhere.
Exactly. And get this. When he did the math, he found that gravity in 5 dimensions could actually be interpreted as gravity plus electromagnetism in our familiar 4 dimensions.
Whoa, wait. So he added one extra dimension, and suddenly he could connect gravity and electromagnetism. 2 of the fundamental forces of nature unified by this unseen dimension. That's huge.
It was a pretty remarkable insight.
It was.
But unfortunately, it didn't really get much attention at the time.
Why not?
Well, the world of physics was kind of obsessed with quantum mechanics at that point.
Yeah, all those weird and wonderful things happening at the subatomic level.
Exactly. And, extra dimensions seemed a little too out there, I guess.
Yeah.
But the idea didn't disappear completely, though, right?
Right.
It kind of reemerged in a really big way with string theory.
Oh, string theory. The theory of everything.
A theory of everything. It tries to explain everything in the universe.
Yeah.
From, the tiniest particles to the largest galaxies.
I've heard it involves tiny little vibrating strings that make up all matter and energy.
That's the idea, but pretty complicated.
Yeah.
And that's actually part of the reason why it was initially met with a lot of skepticism.
Yeah.
You see, to make the math of string theory work, you need more than just the 4 dimensions that we're familiar with.
We have 4.
You need 6 extra dimensions.
6. Wow. That's even more mind-boggling than Kaluza's 5.
Right. So suddenly we're dealing with 10 dimensions. 4 that we know and love, and 6 that are hidden somewhere.
But where could they possibly be hiding? I mean, that's a lot of extra dimensions to just, tuck away.
It's the $1,000,000 question, right?
Yeah.
And for a while, string theory was seen as a little bit too strange, too outlandish because of all these extra dimensions. But then came this pivotal moment, and that was the 1984 Aspen Conference.
Oh, the Aspen breakthrough. Wasn't there, a thunderstorm raging outside while these physicists were working away inside?
There was. It was quite dramatic.
Yeah.
But amidst all that chaos, 2 physicists, Michael Green and John Schwartz, they presented their solution to a major problem in string theory. They proved its mathematical consistency, and it was a real game changer.
Yeah.
And it put string theory and those extra dimensions back on the map in a big way.
Okay, so we've got this mind-blowing idea, right? We've got these extra dimensions, but they're maybe curled up and hidden from our perception.
Right.
But how can we even try to visualize something that's beyond our 3 spatial dimensions? It's like trying to imagine a new color.
It's definitely a challenge.
Yeah.
Maybe think of it this way. Imagine an ant walking on a vine.
Okay.
To the ant, the vine seems like a one-dimensional line, right?
Yeah.
But we know it's actually a 2-dimensional surface.
Oh, I see.
So maybe we're like the ant, limited by our perception and unable to see these tiny, curled-up dimensions.
So it's like we're missing a whole layer of reality.
Exactly. And physicists have come up with some pretty fascinating mathematical shapes that could represent these hidden dimensions.
Okay.
They're called Calabi-Yau manifolds.
Calabi-Yau manifolds. Those sound like like something out of a science fiction novel.
They do. They're these incredibly complex, six-dimensional shapes with all these twists and turns and dimensions that we can't even fathom.
So these Calabi-Yau manifolds, could they be like the actual shape of those hidden dimensions?
It's possible, but there's a catch, and that is there are billions upon billions of different Calabi-Yau manifolds.
Oh, wow.
So it makes it really hard to pinpoint which one, if any, corresponds to our universe.
So even if we could somehow visualize these extra dimensions, we wouldn't know which shape to look for.
Right. It's like searching for a needle in a cosmic haystack.
Yeah.
But is there even any way to detect these hidden dimensions if we can't see them directly?
I mean, that's the question, isn't it?
Yeah, and that's where things get even trippier, but there might be some clues.
Okay.
Some subtle hints that these extra dimensions leave behind in our four-dimensional world.
Ooh, like a cosmic mystery.
Yeah.
What kind of clues are we talking about?
We're talking about particles called moduli.
Moduli.
These particles actually represent the size and shape of those extra dimensions. So think of them as like ripples from those hidden dimensions, making their presence known in our world.
So if we could find these moduli particles, we'd have pretty strong evidence for these hidden dimensions.
It would be a major breakthrough.
It would be.
But there's a catch. Moduli are incredibly weakly interacting.
Weakly interacting, what does that mean?
Well, it means they're really hard to detect.
Yeah.
They're almost like ghosts, passing through walls.
Okay.
We can't create them directly in colliders, like the Large Hadron Collider,
Yeah.
because the energy required would be astronomical.
So colliders are out, but if these moduli are so elusive, where could we possibly find them?
That's a great question, and it takes us all the way back to the beginning, to the Big Bang itself.
Whoa, okay, so picture this, right? We're there, just moments after the Big Bang.
Yes.
The universe is unimaginably hot, dense, and rapidly expanding.
It's chaos.
Total chaos. So how do these moduli fit into this chaotic picture?
Well, physicists believe that during this rapid expansion, during a period called inflation, tons of energy was pumped into the universe.
Okay.
And some of that energy may have gone into creating moduli.
So the Big Bang was like a giant moduli factory.
Exactly.
Oh.
And here's the key. Moduli are incredibly long-lived.
Long-lived, okay.
They don't decay easily.
So they could still be hanging around today, like billions of years later.
That's the idea.
Wow.
And because they interact so weakly, they might have persisted for a while as the dominant form of energy in the universe.
Wait, dominant form of energy. You're saying these moduli, these echoes of hidden dimensions, could have been calling the shots in the early universe.
Yeah.
That's incredible.
Yeah, it's pretty mind-blowing.
But if they've decayed since then, is there any way we could detect the aftermath?
And that's what we'll explore in part 2 of our deep dive.
Okay, sounds good. We'll follow those clues, those whispers from the early universe, and see where they lead us. Welcome back to our deep dive into hidden dimension. Last time we were talking about moduli, those particles that might have come from the energy of the Big Bang and could have been like a big deal in the early universe, but you said they've decayed since then, so where'd all that energy go?
Well, that takes us to another piece of this whole puzzle, and that is a particle called the axion.
Axions, okay.
Yeah, and these axions are super light, very weakly interacting particles, and they were originally proposed to solve a different problem in particle physics, but they've also become like a main candidate for dark matter.
Oh, right, dark matter, the mysterious stuff that makes up most of the universe.
Exactly.
But doesn't interact with light.
Right, it's invisible.
Yeah.
But we know it's there because of its gravitational effects.
So how do axions fit into this whole moduli story?
Well, the idea is that as those moduli decayed, they might have decayed into pairs of axions.
Oh.
So imagine you've got this big, heavy moduli particle, and it splits into two lighter, much faster axions.
So the axions, they inherited the energy from the moduli and just took off.
That's right. And because they interact so weakly, they wouldn't have bumped into much stuff as they traveled through the universe.
They're like these little ghost particles, zooming through space for billions of years, carrying echoes of those hidden dimensions.
I like that.
But if they're so hard to find, how could we ever hope to detect them?
It's a challenge for sure, but not impossible. And that's because, even though axions are weakly interacting, they're not totally invisible.
Okay.
They can interact with electromagnetic fields under the right conditions.
Electromagnetic fields like the ones around magnets.
Exactly. So imagine you've got a powerful telescope pointed at a region of space with a really strong magnetic field, like a galaxy cluster.
Okay.
And if there's this background hum of axions from all those moduli decays, some of them, as they pass through that magnetic field, they might convert into photons, particles of light.
Oh, so they'd be detectable. Wow, so it's like axions disappear and then photons suddenly appear, like a cosmic magic trick.
Kind of. And we can detect those photons, that light, with our telescopes, right? So we'd be seeing this faint glow caused by the conversion of axions, these echoes of moduli decay, which themselves are tied to the structure of hidden dimensions. It's pretty amazing when you think about it.
Yeah, so we could potentially be detecting signals from the very early universe, signals that could tell us about, the fabric of reality itself.
That's the beauty of it. And I think it really highlights the power of theoretical physics.
Yeah.
Like how it lets us make these predictions and imagine possibilities that can actually guide our observation.
Okay, but let's bring this back down to Earth for a second.
Sure.
Why should people listening to this care about all this? What's the big takeaway?
Well, I think the big takeaway is that, our understanding of gravity, which is one of the fundamental forces shaping the universe, it's still evolving.
Yeah.
Like Einstein's theory of general relativity was a huge step forward, but it doesn't tell us everything.
Right, like we still don't really know how gravity works at the quantum level, the realm of the very small.
Right, and that's where the idea of extra dimensions could come in.
Okay.
It might sound strange, but it could be the missing piece of the puzzle that helps us connect gravity and quantum mechanics.
It's like finding a hidden passage in a house, revealing a whole new wing you never knew existed.
That's a great way to put it.
So who knows what wonders might be hidden within those extra dimensions? New particles, new forces, maybe even new laws of physics.
Yeah, the possibilities are endless.
It makes you wonder, like, if we ever confirm the existence of these extra dimensions, how would that change how we view reality? Would we still be stuck in our four-dimensional world, or could we one day, access these hidden realms?
That's a question that has fascinated physicists and philosophers for a long time. Yeah. And it's a reminder that we're still really just at the beginning of our journey to understand the universe.
Okay, well, before we get too lost in these big existential questions, you mentioned earlier that there's another connection between extra dimensions and something that we're all familiar with, and that's the Doppler effect.
Oh, yeah, the Doppler effect.
How a siren changes pitch as it passes by.
Right. It's like as the siren's coming towards you, the sound waves get kind of squished together, so the pitch sounds higher.
Yeah.
And then as it moves away, the sound waves stretch out, and the pitch gets lower.
So like a cosmic ambulance siren.
Right.
Light from distant galaxies. It gets stretched out as the universe expands, so it appears red or redshifted.
Exactly. And the further away a galaxy is, the more its light has been stretched, the more redshifted.
So how does this connect to those moduli particles again?
Well, remember we were talking about how the energy of things moving at the speed of light, like photons, gets diluted as the universe expands because their wavelengths are getting stretched out, right?
Yeah.
But the energy of moduli is different, It's mostly tied up in their mass, not their motion.
Right. They're not really zipping around at the speed of light like photons.
Right. So while the energy of photons gets spread out as the universe expands, the energy of the moduli would have stayed pretty much the same.
Oh, okay.
So for a while, those moduli could have held on to their energy much better than other particles.
It's like they had a secret advantage. So while everything else was getting diluted, the moduli were holding strong, maybe even influencing how the universe evolved.
It's a fascinating thought, right? It shows how these hypothetical particles linked to these unseen dimensions could have played a pretty crucial role in shaping the cosmos as we know it.
And it really shows how complex and interconnected the universe is.
Yeah. Absolutely.
Like there's still so much that we don't know, so many mysteries out there waiting to be uncovered.
Definitely keeps things interesting.
Okay, well, I'm officially hooked on this hidden dimensions mystery.
Me too.
But I think we're running out of time for this segment, so looks like we'll have to save the rest of this cosmic detective story for part 3. All right, so welcome back to our deep dive. We're finishing up our exploration of hidden dimensions, and right before the break, we were talking about, the Doppler effect and how it works with sound, but also with light in the expanding universe.
Right. Yeah. It's like a cosmic ambulance.
Yeah.
As it's moving towards you, the waves are compressed and it sounds higher pitched. But then as it moves away, the waves get stretched out and it sounds lower pitched.
So just like that cosmic ambulance, right?
Yeah.
The light from these distant galaxies gets stretched as the universe expands, and that's why it appears redder.
Right. It's redshifted.
Yeah, redshift.
And the farther away the galaxy is, the more its light has been stretched out, so the more redshifted it appears.
Okay, that makes sense. But I think you were about to connect this to the moduli particles, so Remind me how that works again.
Oh, yeah. So remember we were talking about how the energy of things like photons, things moving at the speed of light, gets diluted as the universe expands.
Right.
Because their wavelengths are stretching out.
Yeah.
But the energy of moduli is different.
Right, because it's mostly in their mass.
Exactly. Yeah, it's not so much about their motion.
Okay.
So as the universe expands and the energy of those photons is getting kind of spread out, the moduli would have stayed pretty much constant.
So, like, they had this advantage in the early universe
Yeah, it's
while
like,
everything else was getting diluted.
well, everything else is getting weaker. They're holding strong.
So they could have had a big influence on how the universe actually evolved.
Yeah, and it's just another way that these hypothetical particles tied to these unseen dimensions could have played a really key role in shaping the cosmos.
It's like a whole hidden layer of the universe.
A hidden layer, that's a great way to put it.
Yeah, influencing things from behind the scenes.
Yeah, kind of pulling the strings.
So I guess to kind of bring it all back to the beginning, we started with this question. What if there is more to reality than we can see? What if there are these hidden dimensions curled up in scales that are just too small for us to see?
Right, like what if there's a whole other world right under our noses and we just can't perceive it?
Exactly. And we talked about all these possibilities, like how those extra dimensions could be unifying forces, or how they might be shaped like these really complex Calabi-Yau manifold, and then how they might have even left traces behind in the form of those moduli particles.
Right, those echoes from the early universe.
Yeah, and even if we never, directly observe these hidden dimensions, I think the search itself is really valuable.
Oh, absolutely.
It's opened up all these new avenues of exploration, really pushed the boundaries of what we thought was possible.
It's all about asking those big questions,
Yeah.
challenging our assumptions and being open to the unexpected.
And you never know, maybe one day, with new technologies, new ways of thinking about things, we'll be able to finally look into those hidden dimensions and really unlock more secrets of the universe.
It's an exciting thought, for sure.
It is. So I guess that wraps up our deep dive into hidden dimensions. Thanks so much for joining us, everyone.
Keep looking up.